Hello viewers. So we have this question that says 0.0785 grams of selenium vapor occupying a volume of 105 mils of 600 degrees Celsius exerts a pressure of 160 millimeters of mercury. The selenium is in a state of equilibrium according to the reaction Se6 giving us 3 Se2. Calculate the degree of dissociation of selenium, the Kp and the Kc, given that the molar mass for selenium is 79. Now we are given data and we've collected it already. So we have the mass of 0.0785 grams, we have the pressure, we have volume, and we have temperature. Now the pressure will be needed in the units of atm, so we converted it. 160 will give us 0.2105 atm. To convert from millimeters of mercury to atm, you divide by 760. Then we have a volume of 0.105 liters. When you convert from mils to liters, you basically divide by 1,000. So when you do that, you're going to get that value. Then converting temperature from degrees Celsius to Kelvin, you just add 273. So that's what we have done there. And we got 873. So now that we have our data in the correct units, we can proceed. Now, the first step we need to do is we need to find the number of moles of selenium, the initial number of moles of selenium. The formula we need for number of moles is still the same common formula. Number of moles is equal to the mass given divided by the molar mass. The mass we are given is 0.0785 grams. That's what we are given. And we're going to divide this by. Now, the selenium we have here, what we are looking for, the number of moles we are looking for is for this component here. So you can see it has got a subscript of 6 here. What that implies is we have 6 atoms of selenium. So the molar mass would be 6 multiplied by 79 grams per mole. So that's what we are going to have here. The number of atoms, which is 6 multiplied by the molar mass. When we do our mathematics there, we must find the number of moles to be 0.0001656 moles. So that's the number of moles we're going to have initially for selenium, 0.001656 moles. After finding the number of moles, the next step we need to take is write the ice table. So we'll write the ice table now. We'll say we have selenium 6, that is changing to 3 Se2 on the other side. Our ice table will have the initial, the change, and the equilibrium part. So now what we do here is on the initial part, we not say initially selenium is going to contain a number of moles, a certain number of moles, and then the other part is going to have 0 because initially we only have this part here. So only have selenium 6 here before it changes to the other part. So we'll have a certain number of moles, an amount of number of moles on this selenium 6 side and the 0 on the other side. Then on the change here, we're going to say 1 minus the degree of dissociation. The reason why we are putting a 1, we are saying 100% of this amount here that we have is going to reduce by a certain amount that we don't know. So 100%, which we are considering to be 1 in standard form, will reduce by a certain amount what we are calling a dissociation amount. So that's what is going to happen there. And on the other side here, we are going to say we are going to have 3 multiplied by the degree of dissociation. Now the 3 comes from the balancing coefficient that we have there. Because of that 3, we are going to have a plus 3 multiplied by the degree of dissociation. This 3 here has got an effect on the change here. If we never had this 3 here, we're going to say we have an addition of just the degree of dissociation there, but because of that number, it also comes down, as you can see. So at equilibrium here, we're going to say the initial amount that we had, which is an initial number of moles, multiplied by the change, which is 1 minus the degree of dissociation. Then on the other side also, it's going to multiply by what we have. So we'll have 3 multiplied by the initial number of moles multiplied by the degree of dissociation, like that. So this is what we are going to have on the equilibrium part. So remember we said we'll have a certain amount that we don't know. We'll call it an initial amount of moles. Then on the other side, we don't have anything. On the change, we are saying 100% of the initial amount will reduce by a certain amount that we don't know. We are calling that the degree of dissociation. Then on the other side, it's going to increase by that amount that is coming out from here, but then it's going to increase by 3 times because we have a balancing coefficient of 3 on the other side. Then at equilibrium here, we are saying the initial number of moles multiplied by the change for each. So we have the initial multiplied by the change, and on the other side, we also have the initial multiplied by the change. So that's what we have at that stage. After reaching here, what we'll do now is we're going to say, we're going to use the ideal gas law equation that says PV is equal to nRT. So we have PV is equal to nRT. Making n the subject of the formula, we'll say our n is equal to PV that will divide by RT, like that. So this is what we are going to have here. Where this n here is going to be calculated from the equilibrium. So we're going to find the total number of moles. This n we have here is the total number of moles. So let's call it NT. NT, even there, let's call it NT. So to find our NT, we'll say this NT is equal to, we'll have the initial multiplied by 1 minus the degree of dissociation added to, we are basically taking the sum of moles at equilibrium. So added to 3, that is multiplying by that. So this is what we are going to have there. Just to write that clearly. So we're going to have 3, then we'll have that multiplied by that. What we have here on the left side is when you multiply n naught by 1, we're going to get n naught. Then when we multiply this by the degree of dissociation, we're going to get n naught degree of dissociation. Then this whole thing is going to be added to 3 n initial alpha. When you do mathematics here, like terms together, you find that we have this and that to be like terms together. So we'll say these are like terms, and we'll say n naught alpha added to 3 n naught alpha. This will give us, this will be equal to, we're going to have n naught added to 2 n naught alpha. This is what we are going to have there. Since we have since we have this to be the same, we have common things here. We have this and we have that to be common, so we can factor it out. We can say n naught is common, so we have our n naught factored out, and then what remains from here, when we get n naught from there, we'll have a 1, and then this will be added to from 2 n naught. When we get n naught from there, we'll have 2 multiplied by the degree of dissociation. So this is basically our total number of moles. N naught multiplied by 1 plus 2 alpha. So this is our total number of moles. And this here is what we are going to put there on NT here, the total number of moles. So doing that, we'll say what we have here now is replacing on the NT there. We'll say we have N initial 1 plus 2 alpha. This will be equal to what we have there is PV over RT. Now, the pressure, if we still remember our data on the other side, we have a pressure of 0.2105, like that. And this is in the units of atm. And this will multiply by the volume we have is 0.105 liters. Then this will divide by our R. R is a constant, which is 0.0821, and this is in the units of liters, atm mole Kelvin, like that. So those are the units. And then this is multiplying by temperature that we said is 873 kelvins. So that's what we are going to have there. That's what we are going to have here. Now remember, we found number of moles earlier on, the initial number of moles earlier on, this number of moles, we found them. We're going to replace them in the next step here. Let's just do mathematics on the other side. So let's say here we still have our n naught, that is multiplying by 1 plus 2, or rather, let me replace it from here so that we don't waste time. Let me replace it from there. So we'll say the number of moles we got, the initial number of moles are 0.00016656, and this is going to multiply by what we have there is 1 added to 2 alpha. Then this will be equated to what we get now as we do mathematics there. Let's see what we get when we punch our calculators there. So when we punch our calculators here, what we get is on the other side, we'll have 3.0832. So 0832. So this is what we're going to get on this side here. It's 3.0832. And this will be in the units of moles. As we cancel here, you find that our atm and atm will go, our liter and liter will go, our Kelvin and our Kelvin will go. And the unit that remains is only moles. After doing this, we're going to make 1 plus 2 alpha the subject. Remember, we are looking for this. We are looking for this here, the degree of dissociation. So we are making sure we leave it alone so that we can find it. So we're going to divide by this value here. We're going to divide by the initial number of moles. And when we do that, what we're going to have here is, we'll say we have 1 added to 2 alpha is equal to 3.08, 3.08, 32 moles. That will be divided by the initial number of moles is 0.001656, also in the units of moles. So this is what we are going to have here. All we have to do again is punch our calculators and see what we are getting after that. So now, what we have is 1 added to 2 alpha is equal to, when we punch our calculator there, we must get 1.8618. So that's what we are supposed to get. And now when we reach this stage, all we have to do is find alpha, and you make it the subject. We'll say 2 alpha is equal to 1.8618. When you take a 1 on the other side, it will be minus, so we'll have minus 1. And our 2 alpha will be equal to 1.8618 minus 1 will just give us 0.8618. And all we have to do here is now just find our alpha by saying alpha will be equal to 0.8618, and this will divide by 2. Our alpha will be equal to, when we divide that by 2, we must get 0.43. 0.431. When we divide that by 2, we must get 0.431. Let me just confirm that we have 0.8618 divided by 2. So yes, we're getting 0.4309. So when we round it off, it will give us 0.431. So this is the degree of dissociation that we are looking for in this question. This is the degree of dissociation that we are looking for. If we're saying the percentage dissociation, would just multiply this by 100, and this would give us the degree of dissociation in percentage form, or percentage dissociation will be 43.1%. So this is basically how you solve for the degree of dissociation given the information like we have here. Now let's look at how we can find the Kp. Now to find the Kp, we'll need to have a new ice table. So let's quickly have our new ice table here, like that. So we are going to make an assumption on this ice table to say initially we have 1 molar concentration for Se6, and we have nothing on the other side here. We have 1 molar concentration for S6, and we have nothing on the other side. Then on the change, this is going to reduce by a certain amount. We don't know, we'll call that one X, and here is going to increase by a certain amount that is also X, but it's going to multiply by 3 because we have it as a balancing coefficient there. So at equilibrium, we're going to have 1 minus X, and here we're going to have 3X in this case. So this is what we're going to have at equilibrium for this dissociation. So now, The next step we need to take is to find the total number of moles at equilibrium. So NT will be equal to the sum of moles at equilibrium, where we have 1 minus x added to 3x. When you do our mathematics here again, you find that minus x plus 3x, this will basically give us 2x. So what we have is 1 plus 2x is our total number of moles at equilibrium. So that's what we are going to have there. After finding the total number of moles, it means we are good to go. Now, so the next step is coming up with our Kp expression. So our Kp expression will be equal to the partial pressure of Se2. This whole thing here will be given to the power of 3, and this will divide by the partial pressure of Se6, and this will be given to the power of 1, which we don't need to show. So this is what we are going to have here. Let me just write this one properly. So we're going to have the partial pressure of SA6 down here, like that. Now, remember, what we basically have here is the partial pressures. Now, if you still remember Dalton's laws of partial pressures, we are also taught to say the mole fraction can help us find partial pressure of a component. So if we have, let's say we have component A that is added to B in a system, if we have A and B, to find the mole fraction of A, or to find the partial pressure of A, the partial pressure of A can be given by the mole fraction of A multiplied by the total pressure of the system. Where this mole fraction we're talking about here, mole fraction of A, is basically the number of moles of A divided by the total number of moles. So this is what we are going to use in our Kp expression. We're going to pick this part here where we're saying partial pressure of a component is equal to its mole fraction multiplied by the total pressure. So let's use that. All right, so our new Kp expression will be equal to, we're going to say, on top there we'll have the mole fraction of Se2 multiplied by the total pressure, and this whole expression here will be given to the power of 3, and down here we're going to say we have the mole fraction of Se6 that is going to multiply by the total pressure as well. So that's what we. This will proceed to be our Kp will be equal to the mole fraction of Se2 will be its number of moles, which is 3x at equilibrium, divided by the total number of moles, which is 1 plus 2x. And this whole thing here will multiply by Pt. Then we'll give the power of 3 to it. Then this whole thing again is going to divide by, we'll say we have 1 minus x, which is the total number of moles for Se6, divided by 1 plus 2x, and this will also multiply by total pressure. So that's what we are going to have here. All we have to do now is replace. After replacing, remember we found the value of x already. The value of x is the dissociation value we calculated earlier on. The partial pressures, the pressure is given in the question already. So we have all the components here. All we have to do is just replace and do mathematics. So let's do the replacements now. Yes, so we'll say Now what we have to do is our Kp is equal to, when we do our replacement, first of all we need to find here, what you're going to do is, where there is x here, you're going to replace the dissociation value that we found. So when you do that, you're going to say 1 minus x, that is going to give you an amount. Then 3x will also give you an amount. So let's do that first, maybe for the sake of understanding. So we'll say for SE6, here we have 1 minus x. And this will basically give us 1 minus the value of dissociation, which is 0.431. And this will give us an amount of 0.569 moles. So these are the moles for SE6. These are the moles for SE6. We can also do the same to SE2. And this will be on SE2, we have 3x. So 3x, this will be equal to 3 multiplied by 0.431, like that. And this is going to give us an amount of 1.293 moles. So these are the moles we have for Sp2. And remember the total number of moles that we found. Nt is equal to, on the other side, we found that our Nt is equal to 1 plus 2x. So we'll say our Nt is equal to 1 plus 2x. And this is equal to 1 plus 2 multiplied by 0.431. And this will give us an amount of 1.862 moles. So this is the total number of moles. This here is the number of moles for Se6. This here is the number of moles of Se2. It means we now have all the amounts we're looking for. All we have to do is replace, and we'll be able to get our Kp. So let's do that. To get our Kp now, say now our Kp will be equal to, on top there we have an amount of 1.293 moles. That will divide by the total number of moles is 1.862 moles, and this will multiply by the pressure of the system that we're given is 0. So have 0.2105 here. The unit is atm. And then this whole thing is going to be divided by, we have 0.569 moles. That will divide by the total number of moles that we have, again, is still 1.862 moles. Just write that clearly. So 1.862 moles, and this will multiply by the same pressure, which is 0.2105 atm. All right. So when we do our mathematics again there, when we punch our calculators, we are supposed to find a Kp value. Now remember this whole thing here is given to the power of 3. We're taking it from our Kp there. You see our Kp here is given on top here is given to the power of 3. The 3 here, you can see it. So you don't forget it. You need to include it everywhere. So we'll say this whole thing here is given to the power of 3. So when we do our mathematics very well there, you find that our Kp value will be equal to 0.0486. So this is the Kp value that we're basically looking for, 0.0486. Yes. So let's go to the last part that is looking for the Kc value. Now that we have the Kp value, it's very easy for us to find the Kc value. We'll rewrite our chemical reaction again. We have Se6 that is giving us on the other side. We have 3 Se2 like that. This is what we have. And then we'll say our Kp, the relationship between Kp and Kc, that Kp is equal to Kc multiplied by Rt given to the power of change in N, where change in N is basically the difference between the number of moles of the products and the number of moles of the reactants. So since we are looking for Kc, we'll make it the subject. We'll say our Kc will be equal to, on the other side, we'll have our Kp that will be divided by Rt, that will be given by to the power of change in N. So all we have to do here is, again, just do the replacements. Our Kc will be equal to, the Kp value that we got is 0.0486, and this will divide by, our R value is 0.0821, and this will multiply by our temperature, which is basically, where is it again? Our temperature is 873. So 873, and this whole thing here will be given to the power of change in N. Now the change in N is just going to be, change in N is equal to 3 minus 1, giving us a 2. Because here on the product side, we only have 3, and here we only have on the right-hand side. So the power we have is basically 2. So when we do our mathematics again, we find that our Kc value will be equal to just 9.46. That will multiply by 10 to the power of minus 6, like that. So that's our Kc value. That's our Kc value. So this marks the end of this video. I hope